The example that we just illustrated simply has the following to say. Mathematically speaking, given a set A comprising of some n elements, let's say A1, A2 up to An, we are considering the set is finite, and then there's a relation R defined on it, and this relation R is known to be reflexive, symmetric and transitive. Okay, then what does this relation do to the set? What do I even mean by this sentence? Relation do to the set. I mean, sounds like some complicated English usage. What can a relation do to a set? You see, I mean, there's nothing that a relation does to a set. You define a relation on a set, but by that I mean this relation classifies the set into type 1, type 2, type 3. Okay, so what do I mean by that? You saw the recent example of friendships, right? Okay, there's a bunch of 100 friends gets classified into several types, or rather what is called partitions. You partition these 100 friends into some disjoint sets. You see, a friend either belongs to the set as a smaller cluster and knows everyone there, or he is completely outside that cluster. Okay, so let's see mathematically what this means. Given an equivalence relation R, which is known to be reflexive, symmetric and transitive, let us see what happens to this set. You will even realize what I mean by what happens very soon. So it's reflexive, which means for every element, that element R A or B belongs to the relation. Correct? A is related to B is what I mean. Right? Okay. I'm sorry, A is related to A because it's reflexive. For any element A is related to A. Correct? We have been seeing that. Quite obvious. Second, symmetric. Whenever A is related to B, B is also related to A. Right? There are many such relationships. A is friends with B, then B is also friends with A. The last one is transitive, which means whenever A is related to B and B is related to C, A is related to C. Now, let me consider this A1 here coming from A. Okay, A1 belongs to A. Now, just in case A10 and A1 were related, let me write this as A10 or A1, then I realize that A1 or A10 is also true because the relation is given to be symmetric. Now, assuming A2 is related to A1, it implies that A2 is related to A10 as well. Right? So recollect the previous example. A friend's friend is all we mean by transitive relation. A relation R satisfying this, what it does is whenever A1 is related to A10, we will put A1 and A10 into a set. Let us call this set S1. Okay, when A1 is related to, let's say, A2, we'll put that also inside and we say every element here is related to each other because it's a transitive relation. Do we remember from the previous example that when a friend knows someone, when E knew D, E knew the whole of ABC in the previous example, right? So on and so forth, you will get the set S1 to be equal to some elements where everyone know each other. And then take an element that is not inside S1. Okay, let's call it, let's say, some A21 and see what A21 is related to and put that element here and keep going and you will get a brand new set. As you can see, none of the elements of S1 will be related to none of the elements of S2. Why? If in case any element of S1 is related to an element of S2, then the whole of S2 will be related to that element in S1 and S1, S2 will not be two different sets. Please observe that these S1 and S2 are obviously subsets of A. Now, as I keep doing this S1, S2, S3, so on, I should stop somewhere because the set is finite. Set A is finite. So, I will basically be writing A as S1 union S2 union S3 up to let's say SK where a small bouncer ahead, although it's not that big a bouncer, you can understand it, but you will find it difficult to make sense of what I'm saying. I see that this S1, S2 intersection S3 intersection S4 and so on intersection Sk is empty. By that I mean not just is the case that all these sets don't have a common element, no two sets have anything in common. In fact, Si intersection Sj is an empty set. Right? So what is it that we are saying? This here goes the theorem. Given a set A with, let's say, n elements and a relation R which is known to be reflexive, symmetric and transitive, we conclude that such a relation partitions the set into disjoint subsets. So, as and always, whenever there is a property, a theorem, the proof looks a little complicated, but the idea will generally be simple. So I told you the simple version of what the theorem is. You can refer to any book, any standard textbook. The proof will go on the lines that I told you. Okay. So if you're confused, probably you're confused about the notations. The idea is fairly simple. Whenever you have a set and you have a relation R that is an equivalence relation, this R partitions the set A into disjoint sets. Okay. Now, they say the converse is also true. What do we mean by that? By that we mean, if you are given a partition of A as S1 union S2 up to, let's say, Sk, some partition of A, forget about the previous SIs that we wrote, that was in a different context. You simply take A, you classify A as S1, S2 up to Sk. Let's say, for example, you take all citizens of India and classify them based on the states that they belong to. Okay, a person belonging to Maharashtra, people belonging to Karnataka, people belonging to Tamil Nadu are all classified as these sets S1, S2 up to Sk. K is the total number of states in India. Okay, now the converse says, what does the theorem state? If there is an equivalence relation, then A gets partitioned into subsets. One can write it as a partitioning. The relationship in itself induces a partition. The converse would be, if A can be written as disjoint union of some subsets, then you can define an equivalence relation on A such that that induces the given partition. What do I mean by that? Once you see what I'm saying, what I'm going to write next, you'll understand the statement. The converse simply says, A is equal to S1, S2 up to Sk. You can actually define a relation R which is reflexive, symmetric and transitive, and hence an equivalence relation which induces this partition. How do you do that? Very simple. First take S1 and define any two elements in S1 as related. Go to S2 and define any two elements in S2 as related. Okay? Go to S3, ensure that any two elements of S3 are related. So if two elements alpha and beta are present in S3, you say alpha is related to beta and beta is related to alpha. This is your relation. And what you do is, to make it reflexive, you, for every element A in A, you say A is related to A. Okay? Such a relation will induce the given partition. I will not spoon feed any further. This is actually pretty straightforward. As and always, if you're finding it difficult, the problem is with notations. Okay? Go through it a couple of times, you will find it very easy.